Okay, so we'll continue with where we left off last time. So we didn't have a talk yesterday, so let me just try and recap where we were. Over the past, 2 lectures, I tried to point out that you can phrase the information paradox. The modern way of phrasing the information paradox is to phrase it as a conflict between, I mean, that's always been the way, but now it's been made more precise, as a conflict between effective field theory and some general kinds of arguments that you can draw from quantum mechanics. And in particular, we started in the first lecture by saying that if you believe that effective field theory should hold, and that the dual of a generic state in AdS CFT, a generic heavy pure state in AdS CFT is a black hole, and you also believe that a CFT can look inside the bulk and can determine what is happening inside the bulk, then you demand that there should be certain operators in the CFT which have to have certain kinds of properties. And we call these operators A and A tilde, and these A's were, as I said many times in the past few lectures, were both the left and the right movers outside the horizon, and while these left movers could cross the horizon, you needed some new modes behind the horizon, and those were the modes we called the A twiddle. And then the other thing that I pointed out at the end of in the last lecture was that you could construct the A's in a very natural way in the CFT. So it makes sense. You can write down an explicit construction of operators in the CFT that obey all the properties that we wanted from the A's. And so everyone would agree that the CFT can see what is happening outside the black hole. There is not any conflict about that. But then there were these general arguments. They weren't, these broad impossibility kind of arguments which suggested that the CFT does not have enough space to accommodate the A tildes, in that there are no operators in the CFT that can play the role of the A tildes. And I gave you a couple of precise arguments, and I'll give you a couple more arguments now. And let me just remind you, the arguments were, we had this lack of a left inverse argument. And this argument was a statement that A tilde lowers the energy, and so it cannot have a left inverse. Whereas the canonical A tilde dagger lowers the energy, and so it cannot have a left inverse, whereas the canonical commutation relations for A tilde dagger suggest that it should have a left inverse. So it doesn't make sense, or it looks like it doesn't make sense to demand that A tilde obeys the canonical commutation relations and also lowers the Hamiltonian. And then there was this, following along the same lines, we tried to argue that if you computed, this is the occupancy argument, which used the same fact that A tilde dagger lowers H, we tried to argue that if you computed this guy, then you would get something that made no sense. You would get something that looked negative. Okay? And then the last argument I gave you was this NA not equal to 0 argument. And that was the argument that, if you tried to compute trace of NA, and I defined NA last time, it was a combination of the A's and the A tildes, some Bogoliubov transformation that made it the appropriate number observer for the infalling observer. You could compute trace of NA in 2 ways. One of them was by going to the number eigenstate basis of the A's, and then you found the trace of NA you expected to be order 1. And the other was to go to the energy eigenbasis, and you expect all energy eigenstates to be smooth states, and then you found the trace of NA was equal to 0, and so it looked like we had a contradiction. So these were the 3 arguments we discussed, and this is where we are roughly. I'm going to try and give you just a couple of more arguments. So let me call these 1, 2, 3. If you're looking for references, these arguments is in AMPSS. This argument is not in the literature, as I said, but it's easy to construct. And this argument is from Marolf and Pulczynski. Okay. I'm going to give you 2 more arguments, and we'll call them the commutator argument. And I'll talk about the strong subadditivity paradox. Before I go here, I want to say that both of these arguments are not as precise as the 3 arguments we've already discussed, and it's hard to use them and make them mathematically precise and say, look, here you have a contradiction. But nevertheless, they're useful things to think about. And so and strong subadditivity in particular is historically important, because this is how a lot of this recent activity started. And so I will describe it, although as you'll see when I make it, it's going to be much less precise than these 3 arguments. And that's just the way it is. No one has managed to make a very precise contradiction. But nevertheless, there are suggestive arguments which I'll give. Okay, and then in the second half of this lecture, I'm going to switch gears, and I'm going to try and find loopholes in these arguments, and then try and give you an explicit construction of the A tilde in the CFT. And as we'll see, that construction has some rather interesting properties, but we'll do that in the second half. So as I said last time, and I'm saying now, for now and for the next 10 minutes, I have a different hat on my head, and then I'm going to take off that hat and try and argue from the other side. Okay, so are there any questions so far about where we are? This is a good time where if there are questions from the last two lectures, I can take them now and then we can go on. The notes from the last two lectures are online, I think, on the school website, so you can look at them, and I'll put up notes from the two lectures today also online, or Boris will put them up at the end of Okay, great. So let me try and describe now this argument about the commutator. The argument about the commutator is the realization of the following fact. See, one of the things that we demanded from these A tildes was that the cross commutator was 0. So if I write this schematically, we demanded that A tilde commutes with A. So these are new degrees of freedom. Okay? And now you might imagine that the CFT Hilbert space is very big, and the A's are just some operators in the CFT Hilbert space, and so it's very easy to find new operators that commute with these A operators, and that shouldn't be so hard. So the fact that you just want some new degrees of freedom shouldn't be so hard to find. However, the commutator argument is the argument that this is actually not true. Let me just try and tell you, and as I said, this is not a contradiction, but it's a suggestive argument, which is nevertheless a very formidable obstruction if you were to actually try and construct the A tildes. To try and ensure that they really commute with the A's is something that's very hard to do in practice if you try and do it, but as you'll see now, there's no sharp contradiction. Okay? So you might have imagined that because the A tildes in some sense satisfy the same kind of algebra as the A's, you could take some unitary that you find, okay, and write the A tildes as, so I'm being schematic here, so I'm not writing the omega and the k indices. Okay, so I hope that's not causing confusion. So you might imagine that you could take some unitary and write the A tilde as some unitary transform of the A's. Okay? And because you're in such a big Hilbert space and you have a huge unitary, you might imagine that the unitary scrambles up the original operators to some totally different basis, and so that it has a 0 commutator with the old basis. Okay? And indeed, it's true that if you take a generic state, if I define C now as this A tilde U, which is C, then it's indeed true that if you look at the expectation value of C in a state, so this is just a statement you can verify easily. If you take some generic state and you look at the expectation value of C in the generic state, that expectation value is indeed exponentially suppressed. Okay? So it's true that this is e to the minus n squared. Okay? However, if you look at the square of the expectation, or you look at the expectation value of the square of this commutator, if you look at this guy, okay, then this is order 1. And this is the argument that if you look at a generic operator in the Hilbert space, or you try and take these A operators and you try and scramble them so as to get some other algebra of creation and destruction oscillators, then generically you find for some generic U that while it's true that the expectation value of the commutator vanishes, the commutator is not really 0. This is just happening because the commutator has an equal number of positive and negative eigenvalues, and if you look at the square of the eigenvalues, that's something that's order 1. And I won't verify this in great detail here, but you can easily check by taking some unitary and verifying that this is the case. Okay? Now, it's hard to, if you actually try and construct the A tildes, and in fact, many constructions of the A tildes in the literature do fail on this count. You know, they fail on the count that people are not careful about making sure that these new modes that you're constructing, these new degrees of freedom that you're constructing, actually commute with the old degrees of freedom, and so this is something that's important to keep in mind. But if you want to make this really into a contradiction, then that's harder to do. But roughly the way you have to proceed is as follows, and I'll just sketch how you have to proceed. The intuition for the commutator, maybe I should mention the intuition for the fact that there may be no commutator for the A tildes comes from a slightly different position. It comes from thinking of the spin chain. Okay? So let me take a 2-minute detour into the spin chain, which is useful because often people do talk about the spin chain and the information paradox. So let's say you have some spin chain, okay, of n spins. And instead of the A's, you think of the sigmas. So there's, at each index, there's a sigma I A, where A can be x. Oh, sorry, I hope you guys can see at the back. I forgot I had to write bigger. Can you not see it all? I'll write this bigger. Okay. So there's some spin chain, and there are these spin operators at each site. Okay. And there are these spin operators at each site, and this I can go from 1 to n. Okay? So you could think of some model, some latticization of the black hole, where instead of these creation and annihilation operators, you had some spin operators. But now, if you look at these spin operators, then Schu's lemma tells you that even though there are only n of these guys, there are only n spin operators, and this Hilbert space is 2 to the n dimensional. In fact, there are no operators in the Hilbert space that commute with all of these spins. And in fact, you can try and prove some result saying that if you look at the trace of the commutator with all of these guys, mod squared, then this trace, and you sum over all IA, okay, is bounded. I forget the exact number, but it's let me call it 1. Okay. So there's no operator you can find in this space which commutes with all of these spin operators. So if you just try and construct, polynomials of these spin operators and try and find something that will commute with all of these guys, then that's something that's impossible to do in this spin chain. If you want to set up the same kind of contradiction in the CFT, then roughly what you have to do is you have to try and fine grain the frequencies a lot. So let me just try and explain what that means. Now, sometime back, we defined these operators BIs, okay, which were defined as A omega, Fi omega. Okay. And these Fi's were some set of functions which had the property that they had, unit norm. And then if you define a lot of such operators BI, so many operators BI, that the number of polynomials in the BIs, okay, so these are polynomials in the BIs. Okay, it becomes so large that it becomes as big as the dimension of the Hilbert space. And you can check that in order to do this, you roughly have to fine grain your frequencies so that the spacing is about 1 by n cubed. Okay, so if you fine grain the frequency so that the spacing is 1 by n cubed, then you find that the number of polynomials in these frequencies becomes so large that it becomes as large as the dimension of the Hilbert space. And then you could argue that there are no operators that commute with all of these BIs. Okay? But the reason this is not such a sharp contradiction is that somebody might say that you can't really measure all these really fine frequency bands. Okay? And that would be a legitimate argument. And so this is not really a sharp contradiction, and no one has even made this argument precise of trying to construct these polynomials in the BIs, but really this argument about the commutator comes from this intuition of the spin chain, where you find that there are no operators that commute with the ordinary spin operators. So if you want to find a new set of degrees of freedom that lives within the same Hilbert space, you can't find it in the spin chain. And you can try and make some suggestions about why that might be difficult to do in the CFT as well. But what is definitely true is that if you try and take some generic unitary and try and scramble the A operators to get a new algebra, then you will run into trouble because the new algebra will have non-zero commutators with the old algebra. Okay? So this is one more argument. This argument was first, again, articulated in the AMPSS paper, the second paper, which is called an apologia for firewalls. And this argument exists in some form, perhaps not in so much detail, but the argument is stated there. Okay? Okay. Let me then mention the last argument, once again in favor of the fact that the A tildes don't exist, and then I'll switch gears and try and construct the A tildes. Okay. Okay. The last argument is what's called the strong subadditivity paradox, which perhaps many of you have heard. I guess many of you have heard about the strong subadditivity paradox, right? Is there some sense of how many people have heard of it? Or Strong subadditivity paradox. Okay. So not too many. Okay. So I'll try and describe it from scratch. This was an argument that was actually presented first by Mathur. In fact, maybe even in the CERN Winter School in 2009. First in the CERN Winter School in 2009. I'm not sure about that, but this is an argument that comes from Mathur in 2009. I think. And the argument goes as follows. I think it's 2009. And the argument goes as follows. Think of a black hole, and so far we've been thinking in terms of these A's and A tildes, but this argument is not constructed in terms of those A's and A tildes. Okay, it's constructed slightly differently. Think of Hawking radiation happening, and think of the following systems. Think of Hawking radiation as pair production that's happening, okay, at the horizon, which is the heuristic way of thinking of Hawking radiation. Then you have the following setups. You have one Hawking particle which has been produced, and I'll call that particle B. When this pair production happens, you think of it as one particle being produced and going out of the black hole, and some other particle, its partner, being produced and falling inside the black hole. So there's another particle which falls inside, and this guy you call C. And then this is an old black hole, so a lot of evaporation has been happening, and there's some bunch of particles which have been emitted in the past, and the old Hawking radiation I'll call A. So one more thing I should emphasize is that while all the other arguments I mentioned worked for all black holes, okay, didn't really rely on the black hole being much older than the scrambling time, would also have worked for big black holes in AdS. This is an argument that relies on the black hole being old, as we'll see. Okay? So you have a black hole, it was formed in some way, and then it evaporated. It evaporated, so it's emitted some set of Hawking radiation. The gas of Hawking radiation that it's already emitted, we call A, and then it is continuing to emit Hawking radiation. So it's emitting this particle B, which is falling out, and it's emitting this particle C, which is going inside. Okay. Now there are some very general arguments by Page that tell us how the entanglement entropy of this system A has to behave. Okay. And these arguments are extremely general arguments. They rely on nothing but unitarity and genericity of the initial state of the black hole. And they say the following. They say if you look at SA, okay, so this guy A is, even if the whole black hole, so the whole system is in a pure state, okay, but the system A is not in general at some arbitrary point of time in a pure state because it's entangled with this B and C and the rest of the black hole. Okay. So in general, there's some density matrix for A, okay, and you can define SA, which is minus trace of rho A log rho A. Okay. This is the von Neumann entropy of SA. Now you can examine how this SA varies with time, and you find that there's a very general curve you can argue on very general grounds, which is the following. Initially, SA starts at 0. The reason it starts at 0 is that initially the set A is empty. Okay, there's nothing in A. There's no Hawking radiation. Okay, and then A builds up slowly, so it starts building up, and the entanglement entropy starts building up. Okay, so it starts increasing. You also know that finally, at the end of Hawking evaporation, the system is back in a pure state because you assume that you started with a pure state. And so if there's a unitary process that's evolving you from the beginning to the end, then you know that in the end, the system A is back in a pure state. Okay? But then you can say much more, and it turns out if you take a generic state in the Hilbert space and you basically divide it into two parts in almost any possible way you can think of, then you find that this entropy goes up monotonically and it comes down monotonically. Okay? The shape is not a straight line if you really take, you know, but you can rescale the time to make the shape really look like a straight line. Okay? So, and this time here is called the Page time. Okay. Now, and the fact that this curve comes down is simply a result of unitarity, and the fact that this curve has this very, you know, universal behavior is a result of genericity of the state. So there are two things that have gone in. A, you're assuming that the state you're dealing with is a generic state, which you would like to believe because you'd like to say that generic pure states in the CFT or generic heavy pure states are black holes, and black holes are not some very special states. And second, you'd like to believe that it comes back down to 0 because evolution is unitary. If evolution was not unitary, then in the end, SA would be non-zero. Okay? The fact that SA has come back down to 0 and is decreasing is a result of the fact that the evolution of the black hole is unitary. Okay? You're assuming that evolution is unitary. If so, then you can derive the following set of conditions. So imagine that you're at some time. Okay? If you look at A at t plus delta t, okay? So delta t is one time step, then that is going to be A at t, okay, union B. Right? And the reason for that is that this Hawking particle that's being emitted is going to go out and is going to meet this cloud of dust and is going to become part of the new A. Okay? So if you have some A at some t, then after some time the new system that you're going to call A is going to be the old system that you called A plus the Hawking particle that has just been emitted. Okay, so you have this condition. However, if you're on this part of the curve, okay, if you're on this part of the curve, then this is A of t plus delta t, and this is A of t. Okay, therefore, you know that S of A of t plus delta t is smaller than SA, and that's the statement that SAB is smaller than SA. And this is a statement that comes from just unitarity and genericity, as I said. Okay. Then you have the statement that if you look at B and C together, then B and C together are maximally entangled, and a rough way of saying the equations that we've been writing down for how A and A tilde have to be entangled together and have to have cross correlations is the statement that SBC is 0. Okay. So you might think of Hawking radiation as producing EPR pairs, and these two pairs are produced in some state. So if you look at in any individual state that lives in a density matrix, but the two guys together are pure. Okay? So this is the statement which comes from assuming that the horizon is smooth. Smooth, this is unitarity. Okay. And then you have one more statement, which is that SB is equal to SC is greater than 0. And this statement comes simply from the fact that Hawking radiation, you look at an individual Hawking quanta, that looks thermal. Okay? So sorry, when I say SAB, I mean S of A union B. Okay? You take A and B together. And this is the statement that but these three statements are in contradiction with what's called the strong subadditivity of entropy, which is the statement that you look at SAB, okay, plus SBC, and in any system consisting of any three parts, this is always greater than or equal to SA plus SC, okay, whereas here you have just the opposite. Okay. This is called the strong subadditivity of entropy. It's a very general kind of theorem you can prove about for Neumann entropies, but this is you have trouble here because you see that SC is positive and SAB is smaller than SA. Okay, so this part is smaller than this part. SBC is close to 0 and SC is positive, so you're clearly violating the strong subadditivity of entropy. Okay, so this is the strong subadditivity of entropy. Okay, so it looks like some predictions that you might get generically from considering Hawking radiation are once again in contradiction with some arguments, some general arguments from quantum mechanics. Okay. And you see here that you have a contradiction at order 1. The reason this argument was invented was, as I said at the beginning, to try and get rid of the claims that said that you can use 1/n corrections or small corrections to try and get rid of this. And that's because here you see that you have a contradiction at order 1. And the contradiction at order 1 is that SBC is close to 0. So you might say that there are some quantum gravity effects or some string theoretic effects, so SBC is not 0, but it's actually 1/n. You could do that. You could say SC is not log 2, but it's slightly less than log 2. But all that is not going to help you because the contradiction here is an order 1 contradiction. Okay? SA plus SC is greater than SAB plus SBC by an order 1 amount. So if you start playing around with these quantities by 1/n, it doesn't look like that will help. Okay? So this is the strong subadditivity of entropy problem, which was historically first articulated. But as you can see, it's somewhat hard to make precise, and these arguments in terms of local operators are more precise. But we will also resolve this at the end. Okay, so this is all I want to say about various arguments that suggest that the interior of the black hole does not exist. All of these arguments are used to suggest that the interior of the black hole does not exist. In particular, the original suggestion of Mathur and AMPS was drop this. Okay? So drop the idea that SBC is 0. If you drop the idea that SBC is 0 and that the outgoing guy is entangled with the ingoing guy, the moment you drop this, it's very hard to make the horizon smooth. That's like dropping the 2-point commutator of the A tildes with the A's, and as I tried to argue in the first lecture, that's very important to keep the horizon smooth. So if you drop the entanglement between the A tildes and the A's, you don't get a smooth horizon. So this was the suggestion, and the suggestion was that you'd get a firewall, and then these more precise arguments came along from here. Okay, so at this point I'm going to stop, and I'm going to take off my Mathur and AMPSS hat, and I'm going to try and argue from the other side. But before I do that, and I'm going to try and resolve all of these arguments, but before I do that, I'm very happy to take questions here while I still have this hat on. Yeah.
Okay. I think after page time, an external observer also starts getting out information, right?
Yes.
Yeah,
the observer starts so the fact that SAB is smaller than SA is a statement that some information has come out. So the new radiation that's coming out is purifying the old radiation.
Oh, so the observer is already included inside this.
Well, the observer is not so important for this. There's just some gas of Hawking radiation which is getting purified.
Okay.
By the new radiation that's coming out.
I'm slightly confused. I'll probably ask you later.
Okay. Okay, good. So now I'm going to erase all this, and we'll spend the next 1.5 hours trying to resolve all of these paradoxes. Okay. So now what I'm going to do is try and give you an explicit construction of the A tildes, and the plan for the rest of this lecture and for the next lecture, which is after lunch, is to construct the A tildes and show how they're able to exploit loopholes in these arguments. Okay? So I'm now just going to present a construction of the A tildes. I'm going to present some equations, and I'm going to argue that the A tildes are solutions of those equations. The way I'll do it, it may not be entirely motivated why I'm doing this, why I'm writing down some equations, but in about 20 minutes, you should see what the point of writing down those equations were. Okay? So now I'm going to talk about a construction in the CFT. Okay. Before I do that, I think one thing which is very important, and it's in some sense at the core of these resolutions of the information paradox, is that it's important that everything we said about the A tildes is something that came from effective field theory. Okay? So you have to be very careful when you're speaking about this AdS CFT dictionary and trying to put constraints on the bulk from effective field theory considerations, that you also examine the limitations of effective field theory. And whatever conditions that you demand of the A tildes are consistent within those limitations of effective field theory. Okay? So, yes. Yes.
The combination between A and A tilde
yes.
Equal to 0 only in the larger limit, or is it also for finite n?
Okay, so it depends a little bit on how it's defined. These observables are not actually gauge invariant observables. So it's certainly true in whatever reasonable definition that you have that this is true at it's 0 in the large n limit. But the thing is that local observables that you define are not gauge invariant. So if you define them, depending on what gauge you use, you can make this commutator 1 by n, for example. For example, a lot of these commutators are always accurate only to 1 by n, because the precise gauge that you use to define the local observable can change the commutators around by 1 by n. So in fact, in what I'll say, I'll try and construct not the A tildes, but the O tildes, which will exactly commute with the O's, and then you can try and use whatever gauge construction that you have to make a commutator that's either 1 by n or that's 0. But that's I think it's not a gauge invariant question, I think, to ask whether the commutator is exactly 0 or 1 by n. Right. I can describe in more detail if you like later. Okay. So now let me try and first just say some things about limitations of effective field theory. So far we've been considering these correlators. We've actually only considered 2-point correlators in detail, but in principle we could have considered n-point correlators and included some interactions. And we've put various constraints on these correlators, and then we've said from these constraints you do some more expansion of the phi's in terms of A's and A tildes, and you get some properties of the A's and A tildes. However, there are constraints on what kinds of correlators you can make sense of, perhaps even in principle, within quantum gravity. So in particular, it's very important that you keep n is much less than n squared. Okay, if you consider some n squared point correlator, it's not at all clear that you'll get some result that makes any sense from the point of view of effective field theory, or that you should be able to get a result that makes sense from the point of view of locality and various other properties. I'll try and say maybe towards the end of the fourth lecture a little more about this constraint. Okay? It's also very important that all the energies involved, not just the total energy, but all the energies involved are small. So it shouldn't happen that for some 2i's, the distance between these points must always remain larger than 1 by n square. By the way, when I write 1 here, that's because I've set the AdS radius to 1. So this is just a statement that you're considering bulk correlation functions. You should keep the points better separated than the Planck length. Okay? It's also important that you keep the points, you don't make the points separated by too large amounts. So you keep also xi minus xj is smaller than some power of n. Okay? So it's, you don't allow the points to scale, the distance between the points to scale. So you don't look at physics over extremely long time scales. If you do that, then once again effective field theory might break down. So it's important to put constraints on what are the kinds of questions you can ask within effective field theory, and what are the kinds of experiments that an infalling observer can really do. And as you'll see, this is at the heart of resolving a lot of these paradoxes, and a lot of these paradoxes arise because you're not careful about what are the precise kinds of experiments that an infalling observer can do. Okay? So to make this a little more precise, make these constraints a little more precise, what we'll do is we'll take these modes that we had and we'll coarse grain them a little bit. Okay? For example, one thing you could do is you could define a slightly coarse grain mode as your boundary operator t, but integrated over some finite time. Okay, I have to put a 1 by t here. This is precisely like these B modes we were writing. Okay, but this is just a particular coarse graining. I'm just saying the coarse graining here is determined by saying that you can measure this operator on the boundary for some given fixed time, for some large time t, but not some exponentially large time. Okay, not some time that scales exponentially in n. So this gives you some set of coarse grain modes. If you work out what these O omega n's are, you can work them out in terms of the O omegas that really enter in the Fourier transform of O, and these are these O omegas convolved with some particular function. You could of course choose a different function. You might say you don't use a step function, you use some other function, you use a Gaussian fall-off, or you use something else, but all of that is not going to be important. But it is going to be important that there's some coarse graining that you do, which is important, as I said, to put constraints on what effective field theory can measure. This is this constraint. Okay, fine. Then I'll say that you consider polynomials in these guys. So you consider polynomials in these coarse grain operators. By the way, just to lighten the notation, even though I wrote OC here, I'm now always going to talk about these coarse grained operators. So I will not always keep the OCs, but from now on to the end of these lectures, whenever I write an O, I'm always talking about these kinds of slightly coarse grained operators. Okay, where you've put some limits and measurements, so you've taken the infinitely sharp frequencies and convolved them with some slightly smooth function. So even if I forget to write the C, just keep in mind that I'm always talking about operators of this kind which are slightly coarse grained. Okay, so this is a coarse grain. It's a coarse graining because I put a limit in time on how long I can measure. I put this limit in time. Okay, so I consider polynomials in these guys. So for example, what's an example of a polynomial? Okay, this is a polynomial. A product of two of these guys is a polynomial. This is a polynomial. Omega 2 plus some coefficient 1. Okay. Sum of these two guys is a polynomial, and a polynomial is just products of these kinds of modes, okay, and sum together. So this set of polynomials in these coarse grained modes forms a vector space. But I'm going to put some constraints to make these constraints on effective field theory precise. I'm going to put some constraints on what are the kinds of polynomials that you can measure. In particular, I'll translate these constraints here into the statement that if you look at any particular monomial in these polynomials, so there are some monomials that enter into these polynomials, any particular monomial in this polynomial has the property that all these frequencies that appear, okay, if you just look at the sum of all the frequencies that appear, okay, that this is much smaller than n, okay, and also the order of any monomial can't be too large. So you can't take a monomial which has a product of n of these co-strain operators. That was this constraint that we had some time back. Okay? So the total order is smaller than n squared. Smaller than n. Let's just keep it smaller than n. So by the way, I'm writing smaller than n here. I'm not being very precise about the power of n. You could, some of these, okay, but let's just, I'm not going to write an n squared every time, so I'll keep it smaller than n. You could try and play with some of these limits. So these are not very sharp limits, but right now I'm going to consider, cases where you're only taking measurements which have up to n point correlators. You could try and say that this is n to the 3/2, and then the energies are n to the -1/2, and so on. So you can try and play around with this co-straining a little bit, but none of that is important for the essential point that I'm going to try and make. Okay? And then I'm going to call the set of all these polynomials with these constraints that the total energy, so this is the statement that the total energy is much smaller than n, and this is the statement that the total number of insertions are much smaller than n. I'll call this set, I'll call it A. Okay, this is A with something else. And I'll call representatives of these sets some particular polynomial. I'll call it A. I'll sometimes denote some representatives of these sets by A alpha. Okay. The reason for using the symbol A as opposed to P is because these polynomials form an algebra in some sense. They form an algebra because you can multiply two of them to get other polynomials. Okay? But it's not strictly an algebra, and the reason it's not strictly an algebra is because of these constraints that we are putting. So if you take some of these polynomials and keep multiplying them, eventually they'll go beyond the constraints. So it's not strictly an algebra, but morally, if you forget about these edge effects, and they're not important in effective field theory, then these A's form an algebra. So then the statement is that what I'm going to allow you to measure, and this is the important statement, is the following. You will fall in, I'll say you give me a black hole, okay? You fall into a black hole, the black hole is in a state psi. So you take some state in the CFT, you take a state in the CFT psi, and the job of the bulk to boundary dictionary is to predict expectation values of these A alphas. Okay. So these A alphas includes correlators of the A's. As I said, this is the set of all polynomials with these constraints in the individual monomials. And I'm going to say the job of the bulk to boundary dictionary is to predict expectation values of these states, of these guys, in a given state psi. Okay. And it's very important that this is a restriction I'm going to put on the kinds of observations you can do, and this is in fact the restriction, a very reasonable restriction on the kinds of observations that an infalling observer can do. An infalling observer can't measure some endpoint correlator. An infalling observer can't measure something which involves an insertion of energy which is very large compared to the initial black hole energy, because if this person were to do that, there would be a huge back reaction of his measurement, and then it's not at all clear that the resulting process can be described very well as some local process happening in the old geometry. Okay? So this is a very reasonable restriction I want to emphasize, but it's also a very important restriction on the kinds of measurements I'm going to allow you to make. So you give me a state psi, and then I'm going to predict for you correlators of this kind. And these correlators are going to have to involve the A tildes, because the infalling observer could fall inside and could try and measure A tildes, but I'll try and explain how you can measure the A tildes. You can answer questions about experiments of this sort. So are there any questions about this co-straining in principle? And these restrictions that we're putting on the kinds of measurements an infalling observer can do. Okay, fine. So maybe since I have about 20 minutes left, what I will do is I will write down some linear equations, and then I'll solve them. Okay. So now I'm going to define for you these A tildes. I'm going to construct for you these A tildes. Right now, perhaps the motivation for the construction will not be totally clear, but it should become clear in a few minutes. Okay? So I'll define the A tildes as follows. You give me a state psi, okay? And the infalling observer, as we said, can really do experiments on the state psi and on excitations of the state psi by acting with some of these A alpha operators. Okay? So if you think of the state psi, and then there are these descendants of these psis. Okay, you can produce some other descendant. You can produce some other descendant. Okay. Whatever. Okay. There are various such descendants you can produce by doing these reasonable experiments on a state, and the space, and this is a linear space. Okay. This is a linear vector space. And the subspace that I get out of this, I'll call H psi. Okay. So this is the state psi somewhere here, and this is the space that you get by acting on it with all of these descendants and looking at the linear space that you get as a result. Okay. So this space is what we'll call H psi. This is not H acting on psi, it's H subscript psi. Okay. So this is the state H psi. Now I'm going to define for you an operator that acts on this H psi, and that I claim is going to have just the right properties to play the roles of the A tildes. And that operator is defined by the following set of linear equations, and that's as follows. Just for consistency with the literature, instead of defining the A tildes, I'll define for you the O tildes. Okay? So remember, we got the A's by taking the O's and dividing them by some square root of some Green's function. So rather than constructing the A tildes, and also as I mentioned in the answer to Louis' question, I'll try and construct some O tildes, but the relationship between them is very simple. It's just a question of rescaling, and I'll come to that in a second. Okay. So these, remember that the A omegas were defined as O omega by root of G omega, where this G omega was the expectation value of the commutator. The A omegas were just some rescale values of the modes on the boundary. Instead of constructing the A tilde omegas, I'm going to try and construct in some sense, the parents of the A tilde omegas. Okay. So the claim is, consider the following set of linear equations. Okay. So now I'm going to argue that these equations always have a solution about a generic state, and I'm going to construct the solution, and then I'll try and tell you why these O tildes and the A tildes that you get from them have all the right properties to play the roles of the A tildes behind the horizon. Okay. So the first thing to note about them is that this is a set of linear equations. Okay. The reason it's a set of linear equations is that A appears linearly both on the left and the right. So if this basis of this algebra, okay, this algebra, or the set of observables that I call whatever A with two crosses, is a linear space. Okay. So if you could satisfy these linear equations for some basis of the linear space, okay, that would be good enough to satisfy them. Okay. So if you can satisfy this, really for, even though it's written to work with some generic element of the algebra, if you could satisfy it for some basis, where this AI can be A1 to AD, okay, then that would be good enough, because all elements of this algebra can be obtained as linear combinations of this basis. So AI is defined as some basis, any basis you like, and all elements of A alpha are defined in terms of this basis, and this basis, so if you can satisfy it for any one of them, you just take linear combinations, and you see that because the equation is linear, you will have a solution that will work for any element of this algebra A. Okay, so is this clear? This is a set of linear equations. Second, this is a set of consistent linear equations for a generic state psi. It's not a set of consistent equations for any state, but for a generic state, it is a set of consistent equations. And the reason it's a set of consistent equations is that for a generic pure state, you have this condition, which is that A alpha psi is not equal to 0. Okay. This is simply the statement that if you give me a black hole, you can't destroy the black hole by acting on it with a small number of single trace operators. Okay. If you give me a black hole, you can't, there's no way by just doing a few low energy experiments that you can destroy, you can in a quantum mechanical sense, annihilate the black hole operator. In fact, the set of states for which this is true, for which some element of A alpha does annihilate the state, is a set of measure 0. Okay. Okay? So this is true for all except for a set of measure 0 in the Hilbert space of highly excited states in the CFT. There are states for which this is true, for which A alpha psi is equal to 0. For example, we mentioned in the last lecture and also now these eigenstates of these n omega operators. Okay? So if you take an eigenstate of an n omega operator, an eigenstate of A omega dagger A, then clearly that state does satisfy A alpha and psi is equal to 0. In particular, you just take the operator n omega, subtract the eigenvalue from it, and that element of the algebra, which is an element of the algebra, annihilates the state. But the states that are annihilated by A alpha are precisely going to be the firewall states, and those are a set of measure 0. So for a generic state in the Hilbert space, A alpha psi is not equal to 0, and these are in fact the smooth states, and the states for which A alpha psi is 0 are going to be the firewall states. Okay? Now, because this is true, this set of linear equations that I have here is consistent. And the fact that this is true tells you that if you look at the set of vectors that are produced by acting on psi with AI, this is a linearly independent set of vectors. Okay? And that's just because that statement tells you that no linear combination of these vectors is 0, and therefore the set of vectors acting with AI psi, with A going from A1 to AD, is a linearly independent set of vectors. Okay? Now, just elementary linear algebra tells you yes.
Sorry, how did you make the connection with the firewall state?
I did not motivate it. I said they are going to be the firewall states. So right now I'm just considering a generic state for which it's true that A alpha psi is not equal to 0. There are some states for which A alpha psi is equal to 0. For those states you will not be able to define these tildes. That's a set of measure 0. And so that's the reason that we can call them the firewall states. But right now I just made the statement, I didn't motivate it. So you can't solve these set of equations for all states, but for generic states, for all except for the set of measure 0, you can solve them. And so those states have a smooth horizon. There are some states in which you can't solve them. So it's legitimate to expect they're firewall states. It's legitimate to expect that firewalls are a set of measure 0 in the Hilbert space. And that's fine if that happens. Okay. Yes?
What happens if it's not 0, but it's something like 1 over n or something?
Right. So that's a good question. You could ask what happens if it's 1 over n. For now, okay, so that's also something that happens for a very small set of operators. It's true that if A alpha and psi is 1 over n, that's a statement that the state is almost entirely a firewall state. Okay? So it's a firewall state which is annihilated by these A's. It's 1 minus 1 by n of a firewall state plus some 1 by n of a regular state. Okay? So if you have a state which is almost annihilated by the A alphas, that state is a superposition of a firewall state and some other small regular state. Okay, so that's what such a state would be. But for a generic state, A alpha psi would just be something that's order 1.
Sorry.
Yes.
So are you going to define this measure at some point, or?
Define a measure. Oh, just using the Haar measure. This is a set of measure 0 on the space. I'm not going to define a measure more precisely, but if you just take if you take the set of all states at energy n e to the n squared, and you impose some conditions, so you have an algebra which has a dimension which is much smaller than n squared. So this d here, much smaller than e to the n squared. Okay. And you try and ask how many elements of how many operators drawn from a linear set of this kind annihilate the set of. So the key point here is that the number of elements of this algebra is much smaller than the number of elements of the Hilbert space. Okay. So if you look at these descendants that are produced by taking the state and acting on it with AI, okay, the number of vectors you're looking at are much smaller than the dimension of the Hilbert space. The dimension of the Hilbert space is e to the n squared. Okay. The dimension of this h psi is AI acting on psi, which is d, which is the number of operators you had in the algebra. Okay. So if you take a generic set of d vectors in an e to the n squared dimensional space, okay, these vectors are generically linearly independent. Okay, so if you take some base vector, you act on it with d operators in a bigger Hilbert space, you'll get something that's linearly independent, unless you chose your initial state very specially. Okay. So now just elementary linear algebra tells you if you give me a set of linearly independent vectors, then I can arbitrarily specify the action of a linear operator on a set of linearly independent vectors. Now I can always tell you here are 10 linearly independent vectors, find for me an operator that takes each of these vectors to some other specified vector on the right hand side. Okay, I can always find for you such an operator. I'll write this one down for you explicitly. Okay, but it's just elementary linear algebra that the moment you've proved that these equations are consistent using that condition, you can solve them. But let's just solve them explicitly. Okay. So as I said, you had these states. I'll just lighten the notation. I picked this basis. Maybe I should have used which was AI psi or AM psi. This is the basis of this space H psi. Okay, and this GMN I define as VM Vn. Okay, I define the vectors UM as AM omega dagger e to the minus beta omega by 2 into psi. Okay. And then this O twiddle is defined just by saying twiddle omega is the inverse of this matrix GMN. Okay, so this is an explicit solution to this set of linear equations, but you don't need this explicit solution for anything, but just to point out that it's very easy to write down an explicit solution. Okay. Of course, apart from these O twiddles, we also want to define the O twiddle daggers, and those are defined in a completely analogous way. Those are defined just by saying that dagger on the AI psi is AI into O omega, because if you have a dagger on this side, you don't have a dagger on this side, into psi into e to the plus beta omega by 2. Okay. The general rule actually is, maybe I can write down the general formula. If you want to take the tilde of some operator in this algebra, weight acts on the state, tilde I1, ei2 on psi, ei2, ei1 dagger into e to the minus beta h by 2 into e to the plus beta h by 2 and psi. Okay. So this is the general rule you can use to define the tilde of any element of the algebra. So apart from the element of the algebra, you can use this general rule to define the tilde of any element of the algebra, but we are only going to use these O tildes and these O tilde omega daggers, but you could also define the tilde of O tilde omega 1, O tilde omega 2, if you like, but both of these equations follow from this general rule. Okay? Okay, good. So now we have an explicit solution. Let me just mention one more thing about the Hamiltonian, and maybe since I'm running out of time, I'll try and start next time afresh with how these guys have just the right properties. Okay? Apart from this, I've so far used these elements of the algebra. I haven't said something about the Hamiltonian. Okay? But you can see that because O on a state is like O tilde on a state is like O dagger on a state, and O tilde dagger on a state is like O on a state, you can see that these guys have the wrong commutators with the Hamiltonian. So in particular, you would also like to impose into H, where H is the CFT Hamiltonian, on A alpha psi, okay, is minus omega O tilde omega, okay, on A alpha psi. And of course, this is just minus omega A alpha omega dagger and psi. And there's no problem in imposing this condition in addition to the conditions we've imposed. And if I get to it in the last lecture, I'll try and mention how this condition is important. But it's useful to keep in mind that while the O tildes are in a sense defined to commute with all elements of the ordinary algebras, they have a special commutator with the Hamiltonian. So if you insert the Hamiltonian in this algebra, you have to use you have to make sure that these O tildes don't quite commute with the Hamiltonian, but they have the wrong commutator. Okay, for the ordinary operator, O omega with H is plus omega O omega. That's because H with omega is minus omega omega. Okay, so they have the wrong commutator with the Hamiltonian, and there's no difficulty in solving this set of equations consistently with this commutator. In fact, if you try to put 0 here, then you would run into some difficulties if you try to solve these equations on an energy eigenstate. But with this commutator, there's no difficulty in solving this set of equations. Okay. Okay. So I have a few minutes right now. Okay. So maybe I can say, or maybe I can just start next time. That may be a good a good place to start next time. So let me just recap and we can take a few questions. So let me just recap. I've defined some operators for U O tilde. Right now, it's perhaps not entirely clear what the motivation for defining these operators is, but in the next lecture, I'm going to try and show you how these operators are precisely the right kinds of operators to satisfy all the conditions that we need. In particular, let me also define the A tildes, as I said. So remember, we define this G omega as the expectation value of the commutator of the ordinary guys psi, and the A tilde omegas are just defined as the O tilde omegas by root of G omega. Okay. So I've been writing everything in terms of these O tilde omegas, but these A tilde omegas are just defined in this way. Okay. I'm sorry for leaving you at a slightly unmotivated place, but I'm going to try and explain in the next lecture. We'll just verify explicitly why these equations and the solutions of these equations does have all the right properties that we demanded, and why the solution that we've written down does have all the properties we demanded, and how it works in spite of all the impossibility arguments that I gave last time. And I'll try and explain why it works and why this works despite all of those impossibility arguments. But so far what I've done is I've defined these equations for you, and I've written down some explicit solution, and after lunch we'll come back and see the properties of the solution and see how it does give you a smooth horizon. So maybe we can stop here and take some questions.
So what do you mean by the Haar measure on either the Hilbert space or the algebra?
Oh, so in general, when you speak of the Haar measure, you take some state, you write down the unitary group on it. So you try and generate all states in the Hilbert space by acting on the unitary and some base state, and you write down the Haar measure in the unitary group.
Okay. Is it obvious that such a measure exists in the case where the unitary group is infinite dimensional because the Hilbert space is infinite dimensional?
Okay, fine. So in this case, let's truncate it by looking at the set of states in a given energy and in a certain range of energies, and then there's no problem in defining this measure.
So this approach does not have a Trans-Planckian problem.
Does not have a what problem?
The Trans-Planckian problem. That
right now there's no Trans-Planckian problem. I'm defining the 8 O tilde omegas clearly just as solutions of some linear equation about some state. So there's clearly no Trans-Planckian problem. There's nothing, I mean, it's just a solution of some linear equation about some state. So I didn't need to evolve things back in time. I didn't need to care about, I didn't. So in particular, it's very important. I'm not trying to trace the O tilde omegas as coming from some past state. I'm just saying, give me a state at a time, and I'll tell you how the O tilde omegas are defined in terms of some simple linear equations that are solved at that time. So I'm not trying to do some evolution where I have to worry about how 1/n corrections pile up or anything. It's very straightforward and.
But if I try to evolve it back in time, then will I
get a problem? You should not try and evolve it back in time. If you see, you have to evolve it back in time, you have to understand this Trans-Planckian issue. So in particular, that doesn't. I mean, that's the. Okay, you could try and evolve it back in time. You would get something. But we don't want to enter that question of, what are the very complicated degrees of freedom it came from in the past. Depending on the precise details of the state and the shell that was used to form to collapse it, to get a generic state, you can't even get it by collapse. You have to get it by collapse and then feed it and manipulate it for a long time. So you could try and evolve it back through all of that and you would get something, but it's not of any interest what you would get.
Could you explain or clarify why the algebra is finite dimensional?
So why
the algebra is finite dimensional?
This algebra that I defined?
Yeah.
This algebra I defined to be finite dimensional. So I defined the set of, so I looked at the set of all polynomials. So, I had some set of modes. Sorry, I haven't been writing the C, but I had some set of coarse-grained modes. Okay. So roughly, what you do is you have these O omegas, which is these infinitely sharp frequencies of the O modes. You coarse-grain them a little bit by smearing them. Okay. And then you take some finite set of them. Okay. So you take frequencies at 1/n(q) or 1/n, 2/n, 3/n, 5/n. Okay. And then you look at polynomials in these modes, but I truncated the polynomials by hand. I said, the number of the total energy you allowed is finite, and the total number of insertions you allowed is finite. You can actually easily estimate the size of this algebra. It's just the fact that if you have, if I have m different modes, m different coarse-grained modes, okay, and I allow you t insertions, then the total number of monomials you get is just m to the t. Okay. The total dimension of the Hilbert space is e to the n squared. So it's very easy to ensure that, even if m is very large and t is very large, m to the t, which is d, is much smaller than e to the n squared, which is what was required for all of these arguments.
No further questions? Then let's thank Suvrat again.